So yeah, so just some quick announcements about this. So this is, of course, being recorded and live streamed via Zoom, and the recording will be on YouTube, so you guys can watch it easily in case you need to. And the slides will be available on a PDF. I'll try to check the chat periodically. So someone's already given some questions. How do you integrate a USUB problem if their X is still in it? So we'll take a look at that in a sec. And then should be obvious, but this isn't an exhaustive review. So there may be things that you could be tested go over in this review. But I've tried as best I can to include my internet connection's unstable. Oh no. I've tried my best to include as much as I could in here. It's a 3-hour review anyway. Okay, so we'll just go ahead and get started. So it might feel a little bit like slow in some parts, but I'm trying to like review all things that have gone through that we've covered in this class. So, but I promise I've got some like challenging problems that we can go over. So, okay, so I'm gonna start from the very beginning, okay? So we're back to chapter 1. Okay, so vector is a list of numbers, and that list can be many things. So we've seen it as a velocity vector, we've seen it as a position vector, and there are countless other things that a vector could represent. If you don't want to be frantically writing this whole time, the slides will be available afterwards. Okay, so in this class we mostly deal with real vectors. So, and we underline or boldface them or put like a little harpoon on the top of vectors to distinguish them from just regular numbers. And to indicate that it's a list of n real numbers, we say V is in Rn. So that symbol that we see over and over again just means in, and Rn is written with this sort of weird boldface R, and then an n up like an exponent, and that just is the set of all real vectors with n entries. And vectors can be written horizontally and vertically, and we call them row and column vectors respectively. And they're not the same, and the distinction matters in the context of matrix multiplication. Okay, so questions so far? Okay. Where did that go? Oh. Okay, so vector arithmetic. So it works the way you think it would. You just go component-wise. So let's say we have V and W are in R2. So they're each lists of 2 real numbers. So V plus W, you sort of add them tips tail, right? So there's V plus W. We're seeing that as taking V and putting its tail at the tip of W. And you could do it the other way as well. V minus W, the difference between those 2 vectors, is a vector whose tail is at the origin, right? We consider vectors as being taken from the origin. But if you were to add it to W, you would get to V, right? We can scale vectors. So let's say alpha is some real number. If it's greater than 1, then it's going to make it longer. If it's less than 1, then it's going to make it shorter. And if it's negative, it's going to flip it around, right? So that's vector arithmetic. We can add them, and we can scale them, and we can actually add scalar multiples, and that's what we call a linear combination. Okay, so magnitude. So the magnitude of vector is just the length of that vector. We denote it with these double bars on the sides, and the way we take the magnitude is it's basically just generalized Pythagorean theorem. We take the square root of the sum of the squares of all the entries of that vector, right? And if it has length 1, then we call it a unit vector. And oftentimes we want to deal with unit vectors. If we deal with unit vectors in like say a particular formula, oftentimes it ends up being a lot cleaner. So sometimes we have a vector, but we want a vector that points in the same direction but is length 1. So that process of making a vector point in the same direction but have length 1 is called normalizing it. And the way you do that is you divide it by its magnitude. So this vector here, as long as it's non-zero, a V over its magnitude is length 1. Okay, and it points in the direction of V. Okay, I'm gonna try to check the chat periodically to see if anyone has questions. People that are watching the stream of this, I'm probably not gonna unmute people. So if you have a question, If you could just type it in the chat, that would be awesome. And if you feel like you can only say it by unmuting yourself, then just say that in the chat. Okay. All right. So dot product or inner product. So the dot or inner product between two vectors sort of measures how significantly the vectors point in the same direction. And that's a very vague statement, but I'll clarify that in a moment. Okay, so it's this thing. So if V and W are lists of V1 to Vn and W1 to Wn, their dot product is you multiply corresponding entries and add them together, okay? And it's also this right here, the magnitude of V and W multiplied together times the cosine of the angle between them, okay? And then we have some key facts. So one, just to note here, we're adding up a bunch of real numbers. So the dot product is a scalar. It's just a real number. It's not a vector, okay? And second thing is from this here, from the fact that the dot product is the product of their magnitudes times the cosine of the angle between them, the dot product between two vectors is 0 if and only if they're perpendicular or orthogonal. I should say that's actually as long as they're both non-zero, right? Because if one of them is non-zero, well, I mean, that's still technically it's orthogonal. So it depends on how you define orthogonal, but okay, so, and then projection. So what exactly did I mean when I said that the dot product measures how significantly one points in another's direction? So let's say this is V and W. I'm gonna normalize W here. So this is vector pointing in the direction of W, but unit length. And V dotted with that normalized vector pointing in the direction of W is this length here. It's that length there. It's the component of V that points in the direction of W. So a vector dotted with a unit length vector is the amount of the original vector V that points in the direction of that unit vector, okay? And from that, that means that we could scale the unit vector W by that quantity to get a vector that points in the direction W, whose length is that component we talked about. And that's exactly what the projection formula is, right? So the projection formula just comes from a key fact about the dot product, which is this fact here, this fact there. That's a key fact about the dot product. That's what we mean, that's what I mean, to make it more precise, like that's what I mean when I say that the dot product measures how much one vector goes in the direction. It's a very vague way, to say it in English sounds like very vague, but putting it mathematically makes it a little bit more precise. Does that make sense? Okay, cool. So that's the projection formula. Okay. Let's see. Yeah, he said he would try to cover everything. Okay, I was just reading the chat. Yeah, in the chat. I should be covering most of the stuff, but again, it's not exhaustive. Okay, cross product. So the cross product between, oh, why is that showing? The cross product between two vectors, and I'm just gonna assume they're in R3, gives a vector which is perpendicular or orthogonal to both vectors, okay? So this is the big nasty definition. So this is something we do expect you to be able to calculate. So let's say the vectors are ABC and DEF. The cross product is this. And I would double check that this is right. Just to make sure, because there's a lot in this thing. So if I ever write down a formula that you think might be incorrect, chances are it is, so just like say something. There's probably like a minus missing somewhere. Okay. So this is the cross product. The cross product gives a vector which is orthogonal to both vectors. Okay. Key facts, again, I said it's a vector. And the cross product is 0 between two non-zero vectors, if and only if they're orthogonal. And right-hand rule, order matters. Did you guys talk about right-hand rule in class? Yeah, so you can actually see it with this one. If you imagine, I can't really do this kinesthetically for the people that are in the chat, but for the people that are here in the lecture, like if this is V and this is W, then V cross W, I take my right hand, put my palm facing towards V, and then I turn it towards W, like that, and their cross product will point in that direction of my thumb. So if I were doing W cross V To do that, I'd have to flip my hand around, right? If I wanted to do W cross V, I couldn't go this way. I want my palm to be facing the second vector. So I go W cross V, and the cross product will face in that direction. So here, that's why V cross W is facing up here, because V cross W pointing up. Does that make sense? Okay, cool. All right, parallelograms, parallelepipeds. Just two quick facts. Good things to know. So the cross product can help us find the area or volume of a parallelogram or parallelepiped spanned by vectors in Rn. So this here is called the triple scalar product, I think. Okay. Can I? Okay. Okay. So I'm sort of going fast, but for the older stuff, because we've seen this and built off of it. Okay. So back to functions, multiple variables. So in Calc 1 and 2, we studied almost exclusively functions of one real variable that output to some real number. So functions from R to R. This just means that's the input space, and that's the output space. So that notation there, f from some space to some space, that's what that means. This is the type of element that it takes in. This is the type of element that it outputs. And there are countless examples of functions like that in the real world. There's some examples, but there are lots of examples of functions that we might want to model where one input and one output are not sufficient. Or I should say one real number and as an input and an output is not sufficient. So for example, I just came up with some examples. So cost of a car rental, that's maybe a function of the amount of time that you rented it and how far you drove it, right? And then it's outputting the cost. So that would be an example of a function in the real world that's from R2 to R, right? Or maybe the exact location of some particle in three-dimensional space at some time. So you're inputting time and you're outputting three coordinates in space. So that's an example of a function from R to R3, right? Temperature and air pressure at some point on Earth. So some point on Earth, if we're assuming we're talking about the surface, then you need GPS coordinates maybe. So that's two inputs, and temperature and air pressure are two different outputs. So it's an example of something from R2 to R2, right? So anyway, the point I'm trying to make is that like functions of one variable aren't enough to deal with the things that we encounter in the real world. So that's why we care about functions of more variables. So a function from Rm to Rn is called a real valued multivariable function. Okay, and that's what we study in Calc 3, right? So first we're just going to study functions of the type from Rn to R, so in particular from R2 to R, right? These are the functions that we have been talking about for quite a bit of this class in the context of surfaces, right? Okay. Oh, I'm maybe gonna disable the video. People are like streaming like video games or something through the, what the hell, guys? This is why we can't have nice things. How do I, oh, God. All right, let me see if I can figure out how to do that. One sec. Okay, participants. You guys suck. Okay, more. Allow participants to unmute themselves. I don't know if they should have that responsibility. No, it says they don't have video. Okay, well, can you guys not use all the bandwidth to stream like videos? They were streaming like who's the ice villain guy from The Incredibles? I saw that for like 2 seconds. What's that guy's name? Frozone. Yeah, Frozone. Okay, anyway, so the graph of a function, oh, I need to hide these controls. Okay, hide these controls. Control, Alt, Shift, H, there we go. Okay, the graph of a function of the form from R2 to R is called a surface, right? So here's an example one. F takes in x, y, and outputs 2x plus 3y. Wait, what's so funny? Oh, the Frozone thing? Okay, so here we see we've got this plane through the origin. Here's another more wild one. So it takes an x, y, it sums up the squares of both of them, and it takes the sine of that, and it's got this wild graph, wild surface. Okay, so sometimes they're difficult to visualize, especially on paper. And on exams, we don't have graphing calculators or access to Desmos or anything like that. But sometimes it's useful to know what the graph of a function looks like for solving some problem related to the function. So how would we know that the graph of this function looks like this without access to those things? So what we can do is we can take slices of it. By taking slices, we are then dealing with a curve in two-dimensional space, and those are easy to put onto paper, right? So that's the idea. And there are three common types of slices. I mean, there are more types of slices that we can take, but I'm gonna give three examples here. So one is slicing with a plane parallel to the XY plane. In other words, taking z equal to b constant. So here's an example. F is this thing. You can sort of see that the graph is this paraboloid. And setting f equal to c, we get the equation x squared plus 3y squared equals c. What does that implicit function give us if we were to plot that in R2? What is x squared plus 3y squared equals c if you were to graph it in R2? Yeah, an ellipse. So just doing that algebraically gives us the idea, okay, taking an arbitrary slice with the plane z equals c, you're gonna get some ellipse of some width, right? Okay, so slices of this particular type are called level curves, right? So when we take z equal to be constant and vary that, and we group all those up and study that big set, we call it a level set, right? So here's z equals 1, there's z equals 2, 3, and you can see that if you take lots of slices, you start to get a collection of curves, and we call that collection the level set. And this gives us a way to study the surface, but in two dimensions, right? We can actually write this down on our piece of paper without ever having to draw a three-dimensional object, right? Let me double check the chat. Frozone. Oh yeah, someone remind. Yeah. Okay. Okay, so that's one type of slice, and this is where topographical maps come from, right? So the idea here is like maybe this is somewhere you want to hike, and along this curve, the elevation is 10. I mean, I don't know what elevation would be 10, like 10 meters or something. It's not 10,000 feet. Maybe it's 1,000 feet. Well, that's actually really high up at the top then. I don't know, but that's the idea, right? Okay. Another type is slicing maybe with x equal to some constant, and this is what we get algebraically. So if you set x equal to 0, you get 3y squared. And 3y squared, if you were to graph that in R2, you would get a parabola, right? So that tells us that a slice with x equal to 0 yields a parabola. And you could take other slices too. You could take slices with like x equal to 1 or something. But 0 often works well just because we often deal with nice functions in this class. And then another one, of course, setting y equal to 0, you get a slice in the xz plane, and here we see that it's x squared. So all these things together get us a picture of what the graph looks like. Okay, good? All right. So these last two slices actually give us some insight into what we now know is the partial derivative. So this is the partial derivative, just the definition, so assuming that it exists. If f is a function from R into R, the partial derivative with respect to, let's say, xi at some point p is the instantaneous rate of change of f, and by that we mean the thing that it's outputting in the xi direction at p. And this is the notation that we use, right? So what I meant by that slice gives us some intuition. Let's go back to f equals x squared plus 3y squared, and let's consider the point on the graph 2, 1, f of 2, 1. Now let's say we want to study the instantaneous rate of change in the x direction. So you can sort of see, I'm going to try drawing on this a little bit. Well, no, I'll just leave it. Okay, so let's take a slice it with y equals 1, and you can sort of see how we're going to be able to define our instantaneous rate of change there. Right there, slicing with y equals 1, in that x direction, we're following along the parabola x squared plus 3. And the instantaneous rate of change along that parabola is just the derivative of x squared plus 3 with respect to x. So that actually helps us define the partial derivative, right? So slope of the tangent line there is 4, and that's the partial derivative at that point with respect to x. So what we're sort of seeing here is that taking the partial derivative there with respect to x for this function of x, y, we sort of treated y as a constant, right? So that's the way we do it algebraically. If you're taking the partial derivative with respect to x, treat all the variables other than x as if they were constant. And second order partial derivatives of function from R2 to R, they give you a similar sort of notion, like in calculus 1 and 2. They correspond to concavity in those corresponding directions. Okay. And if we take the partial derivative with respect to x and then to y, or vice versa, we call that a mixed partial of second order. And a fact that we have, if they exist and are continuous at a point, then they're equal. Okay. Are we good so far? Okay. I know this is all still pretty old material, but I want to cover it anyway. Okay. So now we're on to chapter 2. We've covered chapter 1. Okay, so let's assume we've got a function from R2 to R. The derivative of f, I'm saying quote unquote, called the gradient and denoted with this upside down delta called the nabla, denoted nabla f, gives us the direction of maximum rate of change at a point. And here for a function from R2 to R, it's the partial derivative with respect to x and then the partial derivative with respect to y. We just group those up, put them in a vector. And it generalizes to functions of n variables. We just take the partial derivative with respect to each variable, group them all up into a vector. Okay. So the directional derivative. For a function of 2 or more variables, the instantaneous rate of change at a point will depend on the direction you measure, right? For a function of 1 variable, just a function that we would have dealt with in like Calc 1, when we talk about the rate of change, we're talking about the rate of change with respect to x, right? There's not really any ambiguity. But here, at a point on a surface, you could travel in any direction and talk about the instantaneous rate of change in any one of those directions. So that necessitates the directional derivative. So the directional derivative, at some point x naught, y naught, and some direction d, and I'm writing d as dx and dy. Maybe that was a bad choice because it kind of looks like that's the partial derivative of d, but that's not what I meant. The directional derivative gives us the instantaneous rate of change of f in the direction d at x naught, y naught, and it's just the gradient of f evaluated at your point, dotted with the normalized vector of d. So taking d and making it unit length by dividing by its magnitude. Make sense? Okay. So that's the directional derivative. So let's do a problem. Let f be this thing. Find the rate of change of f at 2, 1 in the direction pointing toward the origin. Okay, so we're gonna have to take a bunch of partial derivatives. So let's start off with that, and let's see how writing with this pen works. I hope this works well. I'm not writing on my screen like Roman. I have this tablet, so my handwriting is probably not going to be as lovely, but I'm going to try my best. Okay, so the partial derivative with respect to x at xy is, okay, well, we have these two terms being multiplied, x squared plus y squared, and e to a bunch of stuff. That's a function of x. So we have to use product rule here. We're going to take first the partial derivative of the first term with respect to x. So, I'm not writing on the same thing. So we have 2x, and then times this whole thing. And plus, we have x squared plus y squared. Don't take the derivative of that. And now, take the derivative of this thing. So the derivative of e to the something is e to that something times the derivative of that something. So the derivative of the thing inside there is with respect to x is negative 2x. And then we have e to the negative x squared plus y squared plus 10. Okay? And the partial with respect to y, well, what's nice is that this thing is symmetric with respect to x and y. So the derivative is going to be the same thing if we just swap x and y. So we don't have to think too much about this one. This is 2y, and then times e to the negative x squared plus y squared plus 10 plus, and then x squared plus y squared, negative 2y, and then e to that whole thing. Okay, so we're going to evaluate both of these at 2, 1. So we plug in x equals 2, y equals 1. So we're going to get 4, and then e to the, what is x squared plus y squared plus 10? That's 4 plus 1 is 5 plus 10 is 15. So e to the negative 15 plus x squared plus y squared at 2, 1 is 5. 5 e to the, negative 2 times 1 is negative 2. Oh, I'm sorry, that's the wrong one. That should be negative 4, right? Yeah, sorry. Negative 4, and then times e to the negative 15. So it's 4 minus 20, so negative 16 e to the negative 15. Look good? Okay, and with respect to y, it's the same thing. No, we don't. What am I talking about? We get 2e to the negative 15 plus 5 times negative 2 times 1 is negative 2 times e to the negative 15. And so this is 2 minus 10 is negative 8 e to the negative 15. Okay, so we have both our partial derivatives. And this is asking find the rate of change of f at this point in this direction, and the direction isn't x or y. So we're going to have to use the directional derivative. So directional derivative, we take this gradient that we just found. So the gradient of f at 2, 1 is, we just group both those things up, negative 16 e to the negative 15 and negative 8 e to the negative 15. Okay, we take that and then we take its dot product with the normalized vector in the direction that we want to take the derivative. So what's the direction that we want to take? So we're at the point 2, 1, and we want the direction pointing toward the origin. So let's see if I can draw this here. So here's x, there's y, here's 2, 1, oops. Here's the point 2, 1, and let me change the color here. So the vector pointing toward the origin, be that vector there, d, well, we need the x component to be negative 2, and we need the y component to be negative 1, right? So it's negative 2, 1. Negative 2, negative 1, I mean. Right? So then we normalize this. So let me change it back to black. So d over its magnitude. Well, the magnitude of d is 4 plus 1, so 5. So d over 5. And that doesn't look good. And so we get negative 2/5, negative 1/5. And so the directional derivative is that thing dotted with that thing. So we get we'll get 32 over 5. 30, that's not right. 32 over 5 plus 8 over 5, so 40 over 5. 40 over 5 is 8. So 8e to the negative 15. Sound good? Questions on this? Okay. Yeah. D over, oh, why didn't I take the square root? Sorry about that. Yeah, you're absolutely right. I don't know why I didn't take the square root there. Square root, yeah, my bad, my bad. Thank you for pointing that out. Yeah, people pointed that out in the chat. Yeah, let's just, my bad. Yeah, square root, of course. So we're gonna get 40 over root 5. And you could simplify that if you wanted to, but we don't care about rationalizing these. Okay. Okay. Let me just check the chat real quick. Isn't the magnitude root 5? Yes, it is. Thank you. All right. Okay. So Taylor's theorem. One of the most surprising results of Calc 1 is perhaps Taylor's theorem, maybe. So it tells us that, I mean, I think it's kind of surprising because it tells us that given information about a function just at a single point can get us a really good approximation for the function nearby. So just as a reminder, this is a Maclaurin series because it's centered at the origin. So we have f here, t here at the origin there, that line, that's a linear approximation. That's a Taylor polynomial of order 1. Here, Taylor polynomial of order 2, so it's a sort of quadratic approximation. And these two are the only ones that we're going to deal with for functions of multiple variables, right? So just linear approximations for functions of functions of 2 variables, we call those tangent plane, right? And here, this is sort of like a tangent, what would you call that? Maybe like a tangent paraboloid? Because it's a quadratic, right? And then you can go higher. That's a order 20 approximation. You pretty much get the indistinguishable at this zoom level. Okay, so for a multivariable function f from R into R, we can form a Taylor polynomial which approximates f of p plus h. So p is the point at which we know information about f, and h is some displacement vector. So if f is from R into R, the first order approximation of f at p is f at p plus the gradient of f at p dotted with that displacement vector h. Okay, and actually if you wrote this out for a function of 2 variables, you'd get exactly the equation of the tangent plane. The second, so just as a reminder, when we say f is ck, we mean that it has continuous partial derivatives up to and including order k. Okay. And for second order, it's the same thing for the first 2 terms, f at p plus the gradient of f dotted with that displacement vector h, plus 1/2 of this bigger thing, the second order terms. So this here, did I already? Oh, I accidentally I moved my slides around right before right before this, and I think I might have moved this before the matrix of partial derivatives. So my bad. But this here is the matrix of partial derivatives. So we're supposed to cover that. Okay. So not the matrix of partial derivatives, the Hessian. My bad. Okay, and for functions from R2 to R, you have f at p plus h is f at p plus this guy here, which is just the equation of the tangent plane. And then here, this would be the tangent paraboloid, I guess. Okay. So we're probably not going to expect you to do this in the case of, like, say, a function of R3 or higher. But for a function of R2, we could ask you for the first order or second order approximation, right? And maybe, like, I don't know, maybe we gave you these values and we just wanted you to assemble them all together or something. Or maybe you just have to do it from scratch. I have no idea. But, okay, questions on this? Okay. And then there's an alternative way to write these. So here I'm writing this as f at p plus h is blah, 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 blah. And this is in terms of p and h. So p, the point at which we know things about f, and h being that displacement vector. We can write this as, instead, in terms of just you're inputting some vector x. And now h is x minus p. So this is an alternative formula, but they're defining the same thing. All right. Questions? Yeah.
Wait, aren't the terms for the second order, aren't they like x minus, like the gradient times x minus p squared? Why is it dotted twice with an x minus p term? Because you have x minus p to the t, then you got it with the second order gradient, and then you got it with x minus p again.
Mm-hmm.
Like, let's say you have a series centered at pi over 2, I mean, like 0, and then you try to find the approximation of pi over 2. Isn't it just multiplied by like x plus pi over 2 squared?
So x minus p there is just h, right? X minus p is h. So this and this are identical. We're just replacing h with x minus p. X minus p is that displacement vector.
My question is
yeah.
like, isn't it just 1/2 h to the t dot the second order gradient?
No. Right, I mean, go down here. Down here, you agree that this is the formula for the second order?
Oh,
right?
Yeah.
So this is where these come out. Yeah, this is where these come out. You get two H1s here because of that, that dot product there. So these are the things that we really care that you know, the first and second order for a function of two variables. We're not gonna have you do that for a function of higher variables, I don't think. I mean, I wouldn't guess that you would. So someone asks, when do we need to add the R at the end of, so someone asked, when will these slides be posted? I'll post them right after this. And someone asked, when do we need to add the R at the end for Taylor approximation? So notice here that I put, let me get this with my pen, one sec. So notice here that I put approximately, right? This little twiddle. So that means it's approximate, it's not exact, right? It's just like the Taylor approximation for function one variables. Nearby that point, you get a maybe pretty good approximation, but as you move away, that approximation potentially gets worse. And to have them be equal, you have this remainder term. I don't think you guys ever actually had to calculate the remainder term. And okay, yeah, people in the class are shaking their heads. So I don't think you should expect to have to find the remainder term. We're okay with just finding the approximation. So person in the chat. Okay. Questions on this? Yeah.
So we should just think of it as like an extension of like the equation of the tangent plane.
Yeah. Equation of the tangent plane, you're getting a plane whose first order derivatives match the function. So you're getting an approximation of the function whose first order derivatives match that function. And the tangent quadratic matches the concavity at that point. So yeah, it's an extension, exactly. Okay, so let's do a problem. Okay, so let G be this. Find the degree 2 polynomial which best approximates G near that point. Okay? All right, so let's just start off with, so we're gonna find the degree 2 polynomial, so we're gonna need to take a bunch of partial derivatives. So let's just go ahead and start with that. So G, partial derivative with respect to X. I'm gonna leave a bunch of room here. So G, partial derivative G with respect to X is, okay, we have sine of xy, so we're treating y as a constant. So we get y cos of xy, and then we have minus 6x log of y, and then that one is constant. And let's take the partial with respect to y. We get x cos of y, sorry, cos of xy, minus Okay, so here 3x squared, we're treating that as a constant, and we take the derivative of log of y. So we're going to take the reciprocal here. So we get 3x squared over y. Okay, and we could plug in pi over 2 and 1 there, but let's just go ahead and find the second order partial derivatives too. So second partial with respect to x. So we're going to get negative y squared. Oh, my pen's wigging out. What the heck? Sorry, my pen just wigged out. Let me go back. Where am I? Oh yeah, negative y squared. My pen is doing something weird. Oh, that's weird. Okay, I guess I'm going to write bigger. Okay, sine. Oh, that's disgusting. Why is it doing that? I'm sorry, guys. Let me restart my little tablet thing. Maybe that's what it is. Sorry, hold on, people in the chat. I don't know what the deal with that was. Let's try this again. Let's try this again. There we go. Okay, oh no, that's not better. Damn it, okay. Well, I'm just gonna write it big. So negative y squared sine xy minus 6x over y. And second order partial with respect to y is negative x squared sine of xy minus positive 3x squared over, sorry. Yes.
The negative 6x over y.
Yeah.
Aren't we doing?
Oh, I'm sorry. My mind was on the fact that my tablet is wigging out. I'm sorry, I'm distracting myself. Minus 6x. Darn it, this is frustrating. Okay, minus x squared sine of xy. All right, let me focus. So this here, that's y to the negative 1. So we're going to bring down that negative 1, and that becomes to the negative 2. So this is plus, oh geez, 3x squared over y squared. Okay, God, that was horrible. And now we take the mixed partial. So gxy. So let's do maybe, yeah. Yeah, 6 log y. I'm sorry. I got a little sidetracked. Yes, absolutely. Thanks. Sorry about that. Oh, and my pen's working normal again. So basically, I'm in presenter view, just like this pen, it will map onto my entire screen, but what you're seeing here is like only a portion of my screen. And if I don't restrict that portion of the screen, then it writes on the whole thing. So, but for some reason it stopped restricting, so my pen was acting weird. Now it's acting normal again, so back to it. So partial, the mixed partial, we will maybe take the partial of the partial of g with respect to x with respect to y. So we'll use product rule here. So we'll get cosine of xy, much better, minus, so now we take the derivative of that cos xy term. So we get xy sine of xy. So that's using product rule. And then minus 6x log y. So we're taking the derivative with respect to y. We have minus 6x over y. Okay, so now we just plug in pi over 2 and 1 into all these guys. So gx at pi over 2 and 1. So we're replacing x with pi over 2, y with 1. So let's do this first one. So y is 1, cos of pi over 2. So cos of pi over 2, that is 0. Minus 6 times pi over 2 log of y, which is log of 1, which is 0. So that's also 0. Okay. And now we take partial with respect to y, pi over 2 and 1. And we'll get, okay, at x equals pi over 2. So pi over 2 cos of pi over 2, that's 0, minus 3 times pi over 2 squared, all over 1. So that's just minus 3 pi squared over 4. Okay? And now, second order with respect to x, pi over 2 and 1. So we get negative 1 sine of pi over 2. Sine of pi over 2 is 1. So we get negative 1. To people in the chat, yes, it's being recorded. It's going to be uploaded to YouTube. Minus 6 log of 1, which is 0. Okay, gyy at pi over 2 and 1. We get negative pi over 2 squared, sine at pi over 2. So this is negative pi squared over 4 plus 3 times pi over 2 squared over y squared. So that's 3 pi squared over 4. Negative pi squared over 4 plus 3 pi squared over 4, we get 2 pi squared over 4 or pi squared over 2. And last one, g mixed is, okay, cos at xy, that's cos of pi over 2, which is 0. And then we have xy, sine of xy, so that's minus minus pi over 2, minus 6xy, so minus 6 times pi over 2 is minus 3 pi over 1 is still minus 3 pi, so minus 3 pi. And we could simplify that a little bit. So this is minus 6 pi over 2, so we get minus 7 pi over 2. Okay, so the majority of this problem, as you can see, is we just took a bunch of partial derivatives, right? Now we just need to assemble this in the right way. Okay, so the second order Taylor polynomial of g at the point pi over 2, 1 is, we just assemble this. So it's g at, I'm not going to write out the whole formula. The formula is, you can get that directly from this page, right? It would be this guy right here, the second order one. So we're just going to write that out. Okay, so we have g at, oh, and we didn't get g at pi over 2. G at pi over 2, 1 is, okay, sine of pi over 2 times 1 is sine of pi over 2 is 1 minus 3 times pi squared over 4. So 3 pi squared over 4, log of 1 is 0. And then, so that's minus that, and then plus 1. So we get 2. Okay, so now let's write it out. So the Taylor polynomial of order 2 is 2 plus the first partial of g with respect to x at our point, which is 0, plus second partial is negative 3 pi squared over 4. And then I'm going to write this using this form instead of using this form. I'm going to write it as our input vector is x. And so I'm letting x1 here. I should have said here x1. So I'm going to write this here. X here is p plus h. Right? X here is p plus h. So oh, right. Yeah, thanks. Hold on here. H1, x minus b. Oh, shoot. This form, hold on. P plus h. Yeah, these here are wrong. These here are wrong. I need to fix these. These are supposed to, these are supposed to be x minus p. Those should be x minus p. So those are actually wrong. So this should be, maybe that's actually what he was trying to point out. Those are wrong. I'll fix those on the slides for people later. So this should be, this is, yeah, that's x minus, no, this is the y term. So it should be y minus 1. Yeah, sorry about that. And now we do the second order terms. So we do plus 1/2. Yeah, I see what he was talking about now. So this is going to be, we're going to have x minus 1. This guy here is -1. X minus pi over 2 is what I should say. Squared times the first partial, sorry, second order partial in the x direction is -1. And then plus 2 times x minus pi over 2 and y minus 1 times the mixed partial, which is -1. Oh, this is 0. Sorry, that's 0. This whole thing is 0. Sorry, this sort of got flubbed. Sorry about that, guys. 2x minus pi over 2. Yeah, sorry about that. I'll fix those. Plus 2x minus pi over 2 and y minus 1. And the mixed partial is -7 pi over 2. Oh no, it is -1. I was Jesus Christ. Sorry guys. This is just getting too messy. I'm gonna fix this and I'll also buy you all flowers. Okay, sorry about that. This got screwed. So for people in the chat that aren't here, this is wrong. These guys here are supposed to be, this should be h, which is x minus p. So each of these guys should say x2 minus h2. This guy here should say x1 minus h1. And that was the mistake. Yeah, my bad. Hey, I figured out what you were talking about. These guys were written incorrectly in this part of this. This should be x1 minus h1, and this is x2 minus h2. Yeah, so that's what the issue was. Yeah, I'm gonna fix that in the slides. This example got fucked, so we're gonna, yeah. Okay, I'll come back to this. Forgive me. Okay. Yeah, it's not 0. I know. I got sidetracked. Okay. We're going to do this later. The idea here is you come up with some function at 2.98 and 2.97 for x and y respectively. That would give you the value of this quantity, and then you form a Taylor approximation of that function at maybe like 3 and 3, and then you plug that in. I'm going to move on because we just got really sidetracked. I will post solutions to that. Huh? Yes, that's the point at which you would find information about f. And then your displacement vector would be whatever you'd have to displace 3 and 3 by to get 2.98 and 2.97. Yeah. Yes, that's right. Yeah, linear approximation would be first order, quadratic would be second order. That's right. All right, so I'll post those on the slides. I'll type them up and stuff. Yeah, that got screwed. Sorry about that. Okay. So other multivariable functions and their derivatives. So other multivariable functions other than types from R into R. For example, there's a function that takes in one real number and outputs a vector in Rn. So we call those paths or curves oftentimes. And we'll also often underline them to emphasize the fact that they are a vector valued function. because they're taking in a real number. So we want to emphasize that they're not outputting a real number, they're outputting a vector. And usually we'll deal with paths from R2, through R2 or R3. And we'll come back to those in chapter 4. And we also have functions from Rn to Rn. And usually we deal with transformations R2 to R3. And I have a little, how do I do just my, I just want to click on this. How do I open that? I don't want to do the laser pointer. I just want to click on it. Okay, there we go. So I just want to pull up this little demo. This is just to get you an idea of what we mean by transformations of R2 or R3. This is just an example of a transformation in R2. So it's taking as input this vector here, but it's outputting another vector. So here's this input vector. It's like 15, 5 or something, and it outputs over here. So you can sort of play around with this and see, like, what happens as you plug in different values for x and y. So these are transformations. So these, it's not so easy to visualize the graph of them per se. Usually what we would do if we wanted to visualize this would be to show the entire x and y plane with grid lines, and then to show what happens to those grid lines under that transformation. So this transformation, the one that I gave you guys, is a linear transformation. And by that, I mean, all we do to inputs x and y is we take linear combinations of them, and you study these in detail in linear algebra, okay? So if you want to study those more, then you can do that, unless you already have. Okay, and matrix of partial derivatives, which I thought I already had. So let's say f is from R3 to R3, so it's taking as input a vector, and it's outputting a vector. So again, it's one of those transformations that I was just giving as an example. So each of those are from R3 to R. The derivative of f, quote unquote, which we call the matrix of partial derivatives of f, is the following matrix. So each row of it is the gradient of each of these functions right here, right? And so that's how you get this big nasty matrix here. And you do the same thing for ones that are, say, from R2 to R2. So that's what we mean when we say the derivative of a transformation like this. And the same thing applies if you say from Rm to Rn. Okay, so just as a review, functions R2 to R, that's how we take their derivative. R3 to R, same idea. For paths, you just take their derivatives component-wise. Okay. And for transformations, we form this matrix of partial derivatives. So that's the three-dimensional case. So those are what we mean by derivative. In each of the cases, when we say derivative, that's what we're talking about. Okay, we good on that? All right. So now chain rule, with this idea of just each type of function has its own derivative, then chain rule actually is pretty straightforward. So the chain rule for functions of one real variable, from R to R, the way we take the derivative of their composition, assuming their derivatives are both defined there, is we take the derivative of f at g of x naught, and then multiply by the derivative of g at x naught. And that idea of taking the derivative of the outer function and leaving the inside evaluated at whatever point you're at, and multiplying by the derivative of the inner function is the same here, except by derivative, we mean gradient or matrix of partial derivatives, and by product, we're talking about a matrix product. But it's the same idea. Okay, so to say derivative, I'm just going to mean derivative as the sort of derivative operator, big D, and the derivative of their composition is D of f evaluated at G. That bar, it's the same bar from calculus, just means evaluated at G, times the derivative of G. So where D could mean something for f that's different from what it means for G, right? So let's look at two special cases. One is if C is a curve in R3 and f is a function of three variables that outputs a real number, then their composition, it takes in a real number and it outputs a real number. Let's look at that example first. Okay, so C is a path in R3, and T gives a temperature at some point in R3. That's just the example that I given. So C, maybe it looks like that, like some sort of coil. I mean, that is what this curve looks like. So it's some path in R3. And then T is a little bit more difficult to visualize. This is a function of 3 variables. At each point in 3-dimensional space, it associates some real number. So what you could maybe think of that as is like a temperature map for like the space that you're in. Like at each point in space, there's some temperature associated to that point. So I'm gonna, oops, I zoomed out the chat. So I'm gonna just show you an example here. So if you set T to be 1, so we're taking sort of like level sets, except this level set is a level surface. So if you set T to be 1, you get the equation of a sphere centered at the origin with radius 1. That's for T equals 2, T equals 3, and T equals 4. And so T composed C is giving us the temperature of the particle along this path at time T. That's what's happening. Imagine traveling along this path, but through this like increasing set of spheres, where along each sphere you have like a different temperature. So that's what's happening here. T composed C is the temperature of the particle at time T. Does that make sense? Okay. All right, so let me go next. So find H prime, that's our goal, find H prime. So there's a couple ways you could do this. Method 1 is to literally just write their composition and then take the derivative. So the reason that will work out is because their composition is a function from R to R, and we know how to take derivatives of a function from R to R. That's the first couple weeks of Calc 1, right? So if we compose them, okay, so into T we plug in C. So we get sine squared plus cosine squared plus T squared. So we're just plugging these guys in for that. And sine squared plus cosine squared is 1, so we just get 1 plus T squared. So the temperature of the particle at time T is 1 plus T squared. And so H prime is 2T. Do you guys see how I got H of T? Yeah? So I plugged each of those in. Into T I plug C, so I replace each X with sine, each Y with cos, and Z with T. Yeah. H prime of T would be the rate of change. So let's look at what H means again. So I'm calling T composed C H. So and here T composed C gives us the temperature of the particle at time T, right? So that derivative would just be the rate of change of that, right? The rate of change of the temperature of the particle at time T. So if you're the particle, it's at what rate is your temperature increasing or decreasing? At what rate is your temperature changing at time T? Okay. Second method is using the chain rule. So the chain rule says that H prime is D of T, the derivative of the outer function evaluated at the inner, times the derivative of the inner function, right? That's just what the chain rule is. Derivative of the outer, evaluated at the same inside, times the derivative of the inner, okay? So we just need to write out what each of these are. So the derivative of big T is the gradient of T, and that's 2x, 2y, and 2z. So the derivative of T evaluated at C is 2x, 2y, 2z evaluated at sine, cosine, and T, and we get 2 sine of T, 2 cosine of T, and 2t. So that whole thing, that's this. That's just like in Calc 1, f prime of g of x, right? That's the same thing. Okay, and the derivative of C, well, the derivative of a path is we just take the derivative component-wise, and we get cos, negative sine, and 1, and now the chain rule says that we just take their dot product. So that gradient dotted with that vector, and we get 2t. We get the exact same answer. So obviously in this case, this seems a little bit more involved, but the reason why we could do this in this instance is because why it was easier is because we got a function from R to R and it ended up being super clean, right? 1 plus t squared is a no-brainer to take the derivative of. But maybe the composition, if you write it out in just a function from R to R, maybe it's a really nasty function to take the derivative of, and using the chain rule for multivariable functions ends up being a little cleaner. Okay, so questions on this? Okay. Yeah.
So where did the 2 sin t, 2 cosine t, and 2t come from?
So we're going to evaluate x at sine of t, y at cosine of t, and z at t. Yeah, you see that? Yeah, that's where that comes from. Other questions? Okay. Yeah. I'm sorry, say that again?
He asked if we need to normalize C of t.
Oh, normalize c of t or c prime of t? I mean, neither.
Yeah, because we want to get like the unit change of the t plus and cos like a factor value.
Oh, should this have been normalized? I don't think so. Yeah, I don't think so.
We don't want a unit change. What we want is
Yeah, this is right. Yeah, are you asking if we should normalize this, or are you asking if we should normalize this? C prime t? Yeah, I don't believe you do. I may have spaced out. There was a lot of, yeah, I don't believe you do. But now I'm second guessing myself, so I'm just gonna, huh?
This is the right answer.
Yeah. Oh yeah, and all, that's a good way of checking, because if we were to normalize C,
Then it wouldn't work out.
yeah, this vector has length 2, right? Cosine squared plus sine squared plus 1. So that has length 2. And if we were to divide this by 2, then we would actually get different answers here, right? So that's actually a quick way of double checking. I second guessed myself for a second, but no, we don't normalize that vector there. We get 2t, right? So the chain rule here says that the derivative of h is the derivative of the outer, evaluated at the inner, times the derivative of the inner, right? That's it. That's what the chain rule says in Calc 1, Calc 2, Calc 3, and we just put in what each derivative is for each of those functions.
So we get change of ht based on unit change.
Yes, that's right. Not based on unit change. It's instantaneous rate of change.
Yes.
Instantaneous, yeah. Instantaneous rate of change of t, yes, yeah, exactly. Okay. Other questions? Okay. So let's do one more. Okay, so this one now is we have f from R3 to R, and g is from R3 to R3. And f compose g, I'm going to call that function h. It takes in whatever g takes in, so it takes in R3. Not takes in R3, it takes in a three-dimensional vector, and it outputs a real number. And we're going to find the derivative of h, and the derivative of h, a function from R3 to R, is its gradient, right? So we're finding the derivative of h, the gradient, and again, we can do that two different ways. We can either compose them, so h is f compose g at x, y, z, and it's this thing. And this might get a little gross, but I'm just gonna plug them on in. So gradient of h, we just take the gradient in the way that we usually do. Oops, sorry. And this is it. This is the gradient. so that's just plugging in. Oh, you looked away for 2 seconds and all of a sudden it's filled with algebra. Yeah. So we just took the derivative with respect to x, with respect to y, with respect to z of the composition, and then put all those into a vector, and we've got the answer. So that's method one, just calculating it by composing and then differentiating. Here is using chain rule. So chain rule says that the derivative of h is the derivative of f evaluated at the inside times the derivative of the inside, right? So the derivative of f is the gradient of f, which is 2x, 2y, 2z. Yeah.
So when we compose first and then take the derivative?
Yeah, if you were to do the, yeah, exactly. Not if you're evaluating at a point, then you would plug in the point last, right? Yeah. Okay, so then plugging in g, remember g is y plus z, x plus z, and x plus y. So we replace x with y plus z, we replace y with x plus z, and we replace z with x plus y. And the derivative of g, I'm just going to call each of those components g1, g2, and g3. Then the derivative of g is this matrix of partial derivatives, right? It's a function from R3 to R3. And we get that. So just to make sure we're on the same page here. What happened here is g is a function from R3 to R3. So its derivative is a matrix of partial derivatives, right? What we do here to take the derivative of a function from R3 to R3 is we take the gradient of each one of these entries here. The gradient of this guy is, okay, partial with respect to x of that first term is 0, so we get 0 there. Partial of that first entry with respect to y is 1, so we get 1 there. And then 1 again, and we just do that row by row. So that's where that matrix comes from. Let me check the chat, make sure. Okay. Okay, so the gradient of h is that vector dotted with this matrix. And we get that. And it's actually the exact same answer. So, obviously in this instance, like this is a much longer method, but the chain rule is a good thing to know. I actually gave 2 examples where not using the chain rule is much easier, but let it be known that the chain rule is still useful. Good? Okay, so if you remember anything about that, it's just the chain rule is derivative outside evaluated at the inner function, all times the derivative of the inner function. Okay, so chapter 3, unconstrained optimization for part 1. So remember, for a function of one variable, to find local extrema, we learned that local extrema always occur at points where the derivative is 0, and we call those points critical points. The same thing is true for functions of multiple variables. I'm going to say from Rn to R, except that by derivative we mean gradient, and when we say 0, we mean the 0 vector. Right? So to find the critical points of a function from R2 to R, we set the gradient equal to the 0 vector. That's how we find the critical points. Classifying critical points. We classified critical points. One way we classified critical points in Calc 1 was by using the second derivative test. So we examined the sign of the second derivative at a point, and if the second derivative were negative, then it were a local max, and positive, local min. Oh, I wrote local max twice. That's obviously not true. My bad. The same is true for a function of multiple variables, except that we examine the sign of the determinant of the Hessian. So instead of examining the second derivative, we examine the second derivative, quote unquote, for functions of multiple variables. So the Hessian is this thing, and the determinant of the Hessian is that thing. Oh, that's written wrong. That should be f squared. My bad. Oh, I wrote it right there. Okay, so if f has continuous partial derivatives up to order 2, and x, which I'm writing as x naught, y naught, is a critical point, that is that the gradient is 0 at that point, and we call d the determinant of the Hessian at x, then this is the second derivative test. So if the second order partial with respect to x is negative and d is positive, then it's a local max. Oh, I'm sorry. I wrote, oh yeah, never mind, we're good. And if the second order partial with respect to x is positive and d is positive, then it's a local min. If d is negative, it's a saddle point, and if d is 0, it's inconclusive. So this is the second derivative test analog for functions of multiple variables. If it's inconclusive, it could be any of those, and you would have to use geometry for determining that. Or that's one way you could determine it, is using geometry to determine whether or not it's one of those three. All right, questions? Okay, I'm sorry I'm going fast, but this is a huge slideshow. But actually, we're doing good. We're more than halfway through it, and I think we're, oh, someone asked a question. Why fxx instead of fyy? Oh, you could also do fyy. Yeah, good question. So fyy also works, it's just you don't have to check both. Yeah, good question. I just wrote fxx to make it simple. And it's also the way it's written in your book, I think. Okay, find and classify all critical points of this function. Let's do this. So hopefully my thing is working again. Yes, it's working. Cool. There we go. Okay, so first order partial with respect to x, we get here 2x e to the 1 plus x squared minus y squared. And first partial with respect to y is negative 2y e to the 1 plus x squared minus y squared. So the critical points will occur when the gradient of f, which is equal to this whole thing, is equal to 0. So to have the gradient of f equal to 0, we need both of those components to be equal to 0. So that says, so if we set the gradient equal to 0, that'll happen if and only if 2x e to the 1 plus x squared minus y squared equals 0, and negative 2y e to the 1 plus x squared minus y squared is equal to 0. Okay. So when are these guys equal to 0? Well, the product of a bunch of numbers equals 0 if and only if at least one of those numbers is 0, right? So 2 is not 0, famously. And e to the anything is never 0. And so the only thing that could make these 0 is x or y, right? So this guy equals 0, and that guy equals 0 if and only if x equals 0 and y equals 0. That tells us that 0, 0 is the only critical point. Right? Okay, so now let's classify it. So we're going to use the second derivative test for functions of two variables. So we need the second order partial with respect to x. And there we get 2e to the 1 plus x squared minus y squared plus 4x squared e to the 1 plus x squared minus y squared. And fyy is, let's see, where it's 0, negative 2 e to the 1 plus x squared minus y squared. And we're going to get plus 4y squared. Those negatives multiplied together gave us a positive. Plus 4y squared e to the 1 plus x squared minus y squared. And let's do fxy. Fxy, so we get negative 4xy e to the 1 plus x squared minus y squared. And now we evaluate all of these at 0, 0. That's not an official notation here, but I'm using it. So at 0, 0 there, we're going to get 2e to the 1 plus 0, so that's 2e. There we're going to get negative 2e to the 1 plus 0, so negative 2e. And fxy is negative 4 times 0. So that's 0. Okay? So D is fxx fyy minus fxy squared is equal to negative 4e squared. So what do you guys think? Yeah, it's a saddle point. So we don't have to do any more work here. The negative case is not inconclusive. This tells us that that's a saddle point. Yeah.
So if we have more than one critical point, we just have to determine it for each critical point.
Yeah, that's right. So this is actually, I should say this is D at 0, 0, right? That's D at 0, 0. That's at 0, 0 also. I wouldn't anticipate that you guys would get an inconclusive case. You guys did see that on your homework, but I really wouldn't expect to see it. But what the kind of things you could do would be like, say, take slices. Let's say you get that it's an inconclusive point. I think the one that you guys had on your homework was sine of something, and it moved outwards in this radial fashion. And you could see taking slices in the x and y direction that it looked like a local max, and that was the correct answer for that. Yeah.
Professor Casal said to just say the testing is inconclusive.
Oh, really?
About the answer.
Okay, cool. So, and he would probably like designate that. And if you're unsure, you can ask, oh, you can't ask that in the exam. Well, I guess you could probably message us. I don't really know how it's gonna work, we'll see. Okay, questions on this? Okay, let's skip this for now. We'll come back. Are you guys okay with this? Okay, so chapter 3, optimization. Part 2, constrained optimization. Oh, hold on, I've got questions here. Will you go over 2.4 paths and curves? Yeah, 2.4 gets hashed out in detail, I think, more in chapter 4, and we're gonna talk about that towards the end, yeah, or in the next chapter. Okay, let's say f is from R to R, and require that a is less than or equal to x, is less than or equal to b. So let's say that we're just concerned with finding the absolute max and absolute min of this function in this region, x between a and b. Okay, so you can sort of see here, there's some local extrema. You get those points there. Those are local extrema, points where the derivative is 0. But those are not all of the potential locations for absolute maxima, right? For instance, we see there on the left that the function attains its highest value sort of at that endpoint. So we also have to check those endpoints. And if we choose the largest and the smallest, we get those points there. One of them was local extrema, but one of them wasn't. One of them we actually got at the endpoint. So this is a demonstration of the extreme value theorem. It says that a continuous function on a closed and bounded interval will achieve its, it'll achieve its maximum and minimum values somewhere in that interval. And 2, it's going to occur either at local extrema inside the region, or it's going to occur at the endpoints. So the same thing essentially is true for functions of multiple variables. So again, if it's a continuous function on some closed and bounded region D, then the absolute maximum and minimum values of f are either achieved, well, 1, they are achieved, and 2, they're either achieved at local extrema inside the region or somewhere along the boundary of the region. So it's the same idea as this. It's just inside the region. What we mean by the inside is it might be, say, like a disk or something, or a rectangle, not just a line segment. And the boundary of the region is a curve. in R2, right? It's not just, the boundary of the region here is just these two endpoints. But the boundary of a region in, for functions of multiple variables is a curve in Rn, right? But it's the same sort of idea. Okay, so to find the absolute max and min values of a function on a closed and bounded region D, you check the inside, those are critical points, and take note of the function at each of those points. Then find all the extrema on the boundary of the region, and you pick the largest and the smallest, right? That is constrained optimization. Okay, so let's do an example. So f is from R2 to R, and it's given by this thing, x squared plus y squared plus 2. We're going to find the absolute max and absolute min of f on this region here, D. So what I would recommend doing right off the bat here, do you guys have any guesses? What do you think I'm going to recommend? Yeah, draw a picture. So, I mean, you don't have to draw a picture of the function, but draw a picture of the region. So this region here is a rectangle, right? It's a rectangle in R2, and you can sort of see, okay, here's our function. You don't have to expect, yeah, we're not expecting you to know what this function surface will look like, but here's our function, the surface, and then you can sort of see what happens here if we restrict it to this region. You can already sort of see what the max and mins are going to be. It sort of looks like the min is going to happen on the inside, maybe at 0, 0, as local extrema, and the max, it looks like it's sort of occurring on the boundary at one of those endpoints, right? So we're not expecting you to draw a picture of that, but drawing out the boundary of the region is useful. So I mean something like this. So drawing out the boundary of the region like that. So first thing we're going to do is find all the critical points of the function that lie inside the region. Okay, so just to remind you, f is this, x squared plus y squared plus 2. Okay, so the gradient of f, setting that equal to 0, we get 2x, 2y equals 0. And the only way that that's 0 is if xy equals 0, 0. Is it inside a region? Yes, right? So we only care for constrained optimization about critical points that lie inside the region over which we're optimizing. Okay? So we found that, and let's make note of the value of the function. So at 0, 0, f is 2. Okay, we're going to compare that now to any values that we find on the boundary of the region. So we have 4 borders. So what I'm going to do here, I'm not using Lagrange multipliers. What I'm going to do here is I'm going to incorporate each of these boundaries into our function algebraically. So first thing I'm going to do is I'm going to do y equals -1. So y equals -1 is this boundary right here. So if I plug in y equals -1 and I require that x is between -2 and 1, I get 3x squared. And you can sort of see how the curve is traced out here. There's the curve there. Okay, now it's just like extreme value theorem for functions of one variable. Extreme values on this curve will either occur at local extrema or at the endpoints. Okay, are there any values inside of this segment that are local extrema for that restriction of the function? You can sort of see, I mean, it's 3x squared. 3x squared is a parabola facing up, centered at the origin. So it's going to have a min there at the origin, x equals 0. Not origin, I mean where x equals 0. And then you also have those endpoints, but I'm just going to take the largest of the endpoints. This is 3. I'm sorry, this is 7. And this is, I think, like 4 or something. Yeah, that's 4. So I'm going to take 7 and 3. Okay, you also have that at this corner, 4, but since 4 is between 7 and 3, then we don't care about it. Okay, let's do another one. So if we take y equal to 2, so now we're on that upper part of the square. Y equals 2, then we get 6 plus x squared is what that looks like. And 6 plus x squared, requiring that x is between -2 and 1, it achieves its largest value when x equals 2, right? 6 plus x squared. Here, I'll draw that out on the chalkboard. Other people, you can go on Desmos and graph 6 plus x squared. I mean, 6 plus x squared looks like this, right? And this is between, x is between -2 and 1. -2 is there, 1 is there. And we can now see that it takes its largest value there at x equals -2 and its smallest value at 0. So -2 and 0. This value here is 10 and that value there is 6. Okay, and we don't care about this value because it's neither the max nor the min. Okay, and we check the other ones also. So now we have the only critical point inside the region is 2, and each of these are the largest and smallest values of the function attained on each boundary of the region. So now what we do is we just, oh, why'd the lights go on? Let me turn those off. Lights, low. Said low. Oh, that's too low. Maybe just bright, chalkboard lights off. That's good. So now what we do is we just pick the largest and smallest. The largest is 10, the smallest is 2. And that's consistent with what we thought beforehand, right? We thought that the min was achieved at the origin and the max was on one of those corners, and that's what we're getting algebraically as well. Good? Okay. So this is checking it algebraically, just incorporating each of those boundaries algebraically into your function and then using Calc 1 tools. So the trickiest step was obviously 2, finding the extreme along the boundaries. Sometimes it's a lot easier to use our other tool, method of Lagrange multipliers. So let's say f is differentiable on a closed and bounded region D. If the boundary can be written as the level set of some differentiable function g, then the absolute max and min values of f on, oh, I should say along the boundary of, that's also wrong, I need to fix that. This is supposed to say along the, oops. This is supposed to say along the boundary of D. Boundary of D. Occur only when the gradient of f is parallel to the gradient of g, i.e. that. Okay? Are we good with that? Yeah. Sorry.
Or a square or a rectangle or that. And you don't really need to use Lagrange multipliers, but if you do need to use Lagrange multipliers, it's like a funky shape.
It's not, that's not even necessarily the case, because you could, like, let's say the boundary of the region is like x squared plus y squared equals 1, and let's say your function, you can easily incorporate the equation x squared plus y squared equals 1. Like for instance, like let's say you're trying to maximize like, I don't know, like x squared plus y squared plus 4 or something. Like then you can just incorporate the equation x squared plus y squared equals 1 into your function, just as you would before. But sometimes it's difficult to isolate an x term or a y term when you get something nasty. Yeah, so I don't want to say like that's always the case, that like if it's not a rectangle or triangle, then you need to use Lagrange multipliers, but it's often the case. Yeah, it's often the case. Sort of like a hard and fast rule. All right, other questions? Okay, so let's look at an example. So find the absolute max and min values of this guy, x cubed minus y squared, achieved on that region. So first of all, before we decide that we're going to use Lagrange multipliers, notice that here it looks like it would be kind of challenging to incorporate the, well, I mean, you could isolate the y squared, maybe. If you isolated the y squared, you get y squared is less than or equal to 1 minus x squared. And so you could write g, I'm just going to write this here. You could write f restricted to the boundary of D as x cubed minus, and isolate that, y squared equals 1 minus x squared. So that's x cubed plus x squared minus 1. You could actually do this. you could do this and optimize that. That would be sort of like the original method. But I'm going to do it instead using Lagrange multipliers. But give this a shot. Like, try it and see if you get the same method. There's an example like that the instructor suggested you try. Let me check the chat real quick. Yeah, I already answered that. Okay. Notice that the boundary of D is a level set of some differentiable function g, right? The boundary of D is the equation x squared plus y squared equals 1. And we can write that as a level set of this function g. So that means that we can use the method of Lagrange multipliers. Let's take the gradient of f and take the gradient of g. We get those. Set them parallel, and you get these two equations. So you get 3x squared is equal to 2 lambda x, and negative 2y equals 2 lambda y. So you can solve this a bunch of ways. The way I'm going to solve it is I'm going to multiply each equation by whatever I need to so that the right-hand side with the lambda is the same. So in this case, I need to multiply the top equation by y and the bottom equation by x. And now I get 3x squared y equals 2 lambda xy, which also equals negative 2xy. So that allows me to set both of these equal, and now I no longer have to deal with lambda. 3x squared y equals negative 2xy. So that is going to hold if x or y is 0, and if neither of those are 0, it'll hold if x equals negative 2/3. So we have those, but those are not points. Those aren't points, right? So what do we do with this? Well, this is our region, right? The region is x squared plus y squared is less than or equal to 1. So this is our region, and we're concerned with just the boundary of the region. So this first one, x equals 0, if you plug that into the boundary of the region, you get y equals plus or minus 1. In other words, that's those guys. In other words, I'm intersecting the line x equals 0 with the boundary of the region. And now I get those 2 points. And I plug in those values into our original function that's on the other page, and I get those values. Now, y equals 0, that's this horizontal line. I intersect that with, and you can see where it's going to be. It's at plus or minus 1. But you can also plug it into the function, and you get x equals plus or minus 1. And you find the value of the function at those points. Last one is x equals negative 2/3. And I'm showing you the line here to emphasize the point geometrically. But you can also do it algebraically. If you plug in x equals negative 2/3 into this equation, you get y equals plus or minus the square root of 5/3. And we note the value of the function. And now we're just going to choose the largest and the smallest values. So the largest value is 1, it looks like, right? Yeah, largest value is 1, and the smallest value is negative 1. And notice that we have multiple places where the maximum is achieved. That's a picture of what's going on here. So we have our surface, then restricting it to that disk, you get negative 1, negative 1, negative 1, 1, and then those points here that are neither. And then notice that, oh, did we even check the inside? Oh, we didn't check the inside. You should check the inside. I forgot to check the inside. You can actually see what's going to happen here. You're going to get 0. We should have checked the inside. My bad. I'm just going to write that here. Here, I'll write it here in red. Oops. Why didn't that work? Come on. Okay. And this here, the gradient of f is 0. And the value of the function is 0. So it's neither absolute min or absolute max. So it actually didn't, we still got the answer correct even though we didn't check for the interior. But I'll fix that when I upload these slides. Okay, questions on this? Okay. Yes, of course, yeah. I'm just staying on this last slide for a second. Let me check the chat. Do we need to check the inside if that's a saddle point? Yeah, I mean, because we have the picture, like we didn't need to, but like, yeah, you would totally need to check the inside of that. I just completely forgot to do that. I should, I'll fix that on the slides that I upload. Thank you. Okay. Let me know when you're good. You're good, you don't have to rush. We're just all waiting for you. It's no big deal. No, I'm just kidding. Good, okay. Okay, let's do another problem. So find the absolute minimum and absolute maximum of this function subject to those two constraints. I don't even know if I'm gonna have enough room on this paper. I put the ones that are in the green boxes, I put these up right before I made this, right before we started, and I haven't done them, so I don't know if we'll have enough room for this, but we'll give it a shot. So we're going to use Lagrange multipliers, the method of Lagrange multipliers. But here we have two constraints. And notice that these aren't inequalities. This is actually requiring that both of those are simultaneously true. So x squared minus y squared equals 1, and 2x plus, wait. Oh, yeah, that is right. X squared minus y squared equals 1, and 2x plus z is equal to 1. Okay? So let's see here. So let's take the gradient of f, and we get a nice answer. 1, 1, 1. Right? Gradient of, I'm going to call this guy g. The gradient of g in terms of x and, oh, this should be in xyz, sorry, xyz. This is 2x minus 2y and 0. And if I call this guy h, then the gradient of h is 2, 0, and 1. Okay, so how does Lagrange multipliers work for, the method of Lagrange multipliers work for multiple constraints? Well, the same idea is true. Extrema along the boundary will occur when when the gradient of f is equal to a linear combination, this time, of the gradients of g and h. So I just need to have f written as the gradient of g times some scalar plus the gradient of h times some scalar. Okay, so that tells us that we need to have 1, 1, 1 equal to 2 lambda 1 x, negative 2 lambda 1 y, 0, plus h is 2, 0, 1, so we get 2 lambda 2, 0, and lambda 2. Okay, so here we get three equations. So here we get 1 is equal to 2 lambda 1 x plus 2 lambda 2. 1 equals negative 2 lambda 1 y, and that's it. And 1 equals lambda 2. Okay. So the reason why I said that in one of the previous slides, that there's multiple ways of solving these things is sometimes it's not the best idea to just, you know, like try to get the right-hand sides on all these equations to be the same thing. When right off the bat, we actually see that lambda 2 equals 1. So like, let's just incorporate that into the other equations. Okay, so lambda 2 equals 1, that tells us then that, so I'm gonna bring that up here. We now have that 1 equals 2 lambda 1 x plus 2. And 1 equals negative 2 lambda 1 y. So these two things. So let's look just at, well, there's a couple things you could do. Let's do this. Let's get the right-hand side on both of these equations to be the same. So this then tells us that, so I'm gonna add 2 to both sides here. No, I'm not. I'm going to multiply this by negative x. So 1 and negative x, and here I get 2 lambda 1, and I'm going to multiply this by y. So y equals 2 lambda 1 x y plus 2y, and negative x is equal to 2 lambda 1 xy. And then if I add 2y there, so negative x plus 2y, negative x plus 2y. So now we have that y has to equal negative x plus 2y. So I'm going to bring this over here. So this tells us that y equals negative x plus 2y, and so we get y equals x. Y equals x. So where y equals x, and that's a plane in R3, where y equals x intersects these constraints, that is where we will have our critical points. Not critical points, I should say. That is where potential extrema will occur on this boundary. So y equals x, and now we require that x squared minus y squared equals 1. Okay, well, that's not possible. What? Oh, you did? Oh, yeah. Shoot. That's not good. That's not good.
Just like hypothetically change it to like x squared minus 2y squared, and then it works out.
X squared minus 2y squared? Oh, just hypothetically change it? Yeah. Well, we'd have to change the gradient then. Yeah. Because that was what the problem was.
Yeah, I mean, like, should we calculate the maximum and minimum respectively for each one and find the maximum and minimum?
You add them together with like different constants, because it's with respect to both of these constraints. The intersection of both of those constraint functions is what constrains the general f of x, y, z function.
Yeah, the issue, if it said that constraint or that constraint, then you could just deal with them as two separate problems, right? But it's saying both of those constraints need to be simultaneously applied to the function. So it's not sufficient for just to find like places where the gradient of f is parallel to the gradient of g, or just parallel to the gradient of h. It needs to be parallel to some linear combination of the two of them. Yeah. But I may have copied this problem down or something, or maybe there's some little mistake here. The issue here is that if I incorporate y equals x into, I'm saying this for the people in the chat, if I incorporate y equals x into that first constraint, then we actually get 0 equals 1, and that's an issue. So I guess like that Taylor series problem, just let me come back to this and fix this. I might have just copied the problem down wrong. Sorry, I'll figure it out. My bad, I don't know what happened there. Vector value function, oh yeah, you have a question? Why did we introduce what, sorry? Why do we use the plus sign?
Yeah.
For the to the left of the lambda 2?
Yes.
Oh, well, lambda 2 is an arbitrary constant. So like even if you said, Even if like lambda 2 were negative, the fact that lambda 2 is just an arbitrary constant, we could write plus or minus. Like lambda 2, we're going to find lambda 2 based on that equation. So if we wrote minus and stuck with minus, that would also work.
But like, because what I thought is only, for example, only the gradient of your constraint method is the multiple of the gradient of your original function. So in that case, you're gonna be find the maximum or minimum. So I don't quite get like why we use.
I don't quite understand the question. Let me I may have copied this problem down or have some little algebra mistake here because we're getting a contradiction. So let me address this and I'll fix that in the slides, okay? All right. Okay. So vector valued functions. If f is some curve in Rn, like we said earlier, the derivative of f is you just take the derivative of each component-wise, and the second derivative is exact same thing. So we call f prime the velocity vector of f at t, the acceleration vector. So you can sort of get a picture of what's going on here. Let's say this is f of t going that way, and that's at t star. F prime of t, giving you that velocity vector, giving you the direction and magnitude of that rate of change, and the acceleration vector, which is the rate of change of that rate of change function. Okay. Arc length, pretty straightforward. We just calculate this. There's not really a lot I think we could ask you here. Just calculate some arc length. So if C is a vector valued function in R2 or R3, then the length of the path along C from C at A to C at B is this thing here. So there's a picture of what's going on. Problem, find the length of the curve. So here we're just going to calculate it. Yeah, no worries. Okay, so magnitude of C, let's go ahead and find that. C prime, I mean. Magnitude of C prime here is, we get 1. We'll have to use product rule here. So 1, let's see, sine of t plus t cos of t, and cos of t minus t sine of t. Okay, and now we're going to take the magnitude of this, and so that's going to be the square root of the sum of the squares of each of those entries. So that's going to be 1 plus sine of t plus t cos of t, all squared, plus cos of t minus t sine squared. Sorry, it's t sine of t squared. And I hope this works. Okay, so we get 1 plus sine squared of t plus 2 t sine t cosine t and then plus t squared cos t. And we're going to have a rather large square root here. So I'm just going to, this isn't a fraction, I'm just grouping it all. And then plus cos squared of t minus 2t sine t cosine t, and then plus t squared sine squared t. Okay, so what happens here? Cancellations, which is nice. And we're going to use the fact that sine squared of t plus cosine squared of t is 1. Okay, so now we can write this as the square root of 1 plus, well, we have a sine squared plus cosine squared, so that's 1, so 2. Well, I'll just write 1. Plus, pull the t squared out of the cosine squared plus sine squared, and you get t squared. So we just get square root of 2 plus t squared dt. Oh, darn. We actually, we need to do trig sub, which I don't think you guys will be expected to do. So maybe we won't actually evaluate this integral. Again, I said for the ones in these green boxes, I just pulled these straight from the book. Yeah. Say that one more time.
T squared cosine.
Oh, that's cosine squared. Thanks. Yeah, that's cosine squared. Where is it? There we go. Yeah, so now we're integrating this guy, 2 plus t squared. And this is not something that I think we will expect you to integrate. But the way that we would go about this, I think, would be trig substitution. So if you guys want, I mean, it's technically up for grabs because it's like Calc 2. Unless, has he said explicitly, like, you don't need to know that?
Yeah, he said harder integrals like trig subs will not be on final.
Okay, well then, so this is, so this is trig sub. Not on final. Oops. Yeah. Because let's see. So you would do 1 plus tan squared is secant squared. So you'd let tan be, oh, then you'd have secant cubed, which technically you can integrate secant cubed with a bunch of integration by parts. Anyway, that ends up being a rather nasty one, I guess. Okay. Double and triple integrals. So f, function of two variables. The double integral of f over r, written as that, gives us the sign volume under the surface of f over that region. So we evaluate those by writing them as this iterated integral. So if we write it first integrating in the direction, the x direction and then the y direction, then we have lower and upper bounds on x in terms of y, and then lower and upper bounds on y. Or the other direction, right? So we say a region in R2 is x simple and respectively y simple if every horizontal and respectively vertical line intersects that region in an unbroken line segment. And if it's both x and y simple, then we say it's simple. So let's say this region here. Is this x simple, y simple, both or neither? I'm going to see if I can actually add, I'm going to go to that slide. I'm going to see if I can add a segment and drag it along. That'd be pretty cool. I'm going to insert a shape here, see if that will help. Do you guys see that? Oh, cool, you do see that. Nice. Okay, so I'm going to insert this segment here. I'm going to make it really fat. Okay, and I'm going to make it black. Oops. Okay, so let's drag. Oh, you don't see it as I move it. Okay. Well, let's drag horizontal lines over this. Okay, so it looks like everywhere where it's intersecting the region, it's intersecting it in an unbroken line segment, right? You see where it's intersecting the region? So it's the place where the red and the black segment overlap. So it looks like it's unbroken. Now, intersect it with a vertical line, and it's unbroken, unbroken, unbroken. But then over here, it's intersecting the region in these broken line segments, right? So this thing is x simple. It's not y simple. Oh, I need to switch back to switch the slide. Right, x simple, not y simple. Okay, what about this one? So this one, again, not again, this time it looks like it is y simple, but it is not x simple, right? So that one is y simple. And last one. Yeah, this one it looks like it's both x simple, and if we do the next one, it's also x simple. So it's both y simple and x simple. Does that make sense? Cool. So generally, and there are exceptions to this, because sometimes we will split regions apart and integrate them. Generally, if your region is x simple, then you will want to integrate first with respect to x and then with respect to y. And if the region is y simple, then you'd want to integrate with respect to y, then with respect to x. Again, this is generally true, but there are exceptions. Sometimes we will have some region and we want to like split it into separate regions first. But this is just a general rule of thumb. So here are a couple ways that we could assess your knowledge of this section. So we could give you a region either as a definition, so written out in set builder notation, or we could give you a picture of some region and ask you to evaluate the integral of f over that region for some f. Or we could ask you to evaluate some given iterated integral, and maybe it's not possible to integrate it unless you change the order of integration. So those are two possible ways. Let me check the chat. Lima bean. Oh. Someone said that one of them looked like a lima bean. Good content. Okay. So let's do an example. So evaluate this. Did I even write out parts of this? Okay, yeah, I did. Okay, evaluate the integral of f over r, where f is e to the x squared, and r is the region in R2 where x is between y over 2 and 2, and y is between 0 and 4. So in this case, we're giving you the region, but we're giving you it in set builder notation, not a picture of the region. What I would recommend you do here is draw the region. Draw the region, not the surface, just draw the region in R2 over which you're going to be integrating. And then if you do have to change the order of integration, then you just go to your drawing and you check which variable would be written in whatever way by potentially taking inverses. So let's see how that works here. Okay, so there's our region. You just draw. Oh, this is x between y over 2. Oh shoot, I messed this up. Let me fix this. That's actually wrong. Y over 2 and y is what that should say. Let me fix that. Let me edit that. Y over 2 and y. It's fixing it. There we go. Okay. Okay, so x is between y over 2 and y is between 0 and 4. Okay, so we draw out our region, and I would also recommend writing out, this is y equals x, this is y equals 2x, or x equals y over 2. And if you were to integrate with respect to x first, how would you take the antiderivative of e to the x squared? That's not something that we know how to take the antiderivative of with traditional tools. So instead, we're going to integrate first with respect to y, and hopefully, by doing that, we'll get some additional terms that will allow us to take the integral with respect to x. Okay, so the integral over r is, if we go first with respect to y, then with respect to x, then the lower bound on y is this line here. And this line, written as y in terms of x, is y equals x. This line is the upper bound on y, and written in terms of x, it's y equals 2x. So that's how we get those limits of integration there, from x to 2x, even though those weren't written in the original like set builder form of our region. Okay, and now if we take the antiderivative, we get an additional y out, and then we evaluate y at 2x minus evaluate at x, and we get x. And now it's the perfect setup for doing u sub. So if we let u be x squared, du is 2x dx, then isolating x dx, we get x dx is 1/2 du. So now, changing our limits, not everybody does this, but I personally like to, if I do u sub, I like to actually change the limits to be u at whatever the lower bound on x was, and u at whatever the upper bound on x was. So this is u at x equals 0, which is 0, and u at x equals 2, which is 4, and 1/2 e to the u. And the antiderivative of e to the u with respect to u is u, so we get 1/2 e to the 4th minus 1/2. Yeah, I would say that that's possible. Yeah, I would say that that's not out of the question. Yeah. The question for the people on Zoom was whether or not you could be expected to change the order of integration when evaluating a triple integral. And my answer was that is possible, yeah. Okay, let's do another one. So this time we're given a picture. Oh, why is this showing? I don't want this here. Oops. Go away. And now that's stuck. Okay, I don't know why it's showing that. Sorry, guys. Oops. Control-Alt-Shift-H. There we go. Okay, let's go back. Oh, I didn't make those appear incrementally. Oops. Okay, well, since this region is y simple, let's integrate with respect to y first, and then with respect to x. Okay, so the lower bound on y is this curve in terms of x, which is negative x squared plus 3x. The upper bound is 4. And then we take x from 0 to 3. Okay, so if we take that antiderivative with respect to y, we get y squared over 2, and we evaluate at 4 minus evaluated at that quadratic, and we get this big nasty quintic, and then we take the integral of that. It looks nasty, but this is just a polynomial in x, so we can take the integral. And what we get is negative 117 over 40. Good with that? Okay. Okay, and I think that's, I don't think I actually, yeah, it's been a busy week. I actually did not get a chance to prepare a triple integral section, but we can do problems on triple integrals. We can do whatever you guys want. But I already spent like 1 billion hours on this thing, and I didn't even get a chance to get this part done. So let's do whatever problems you guys want. Also /now is like a time when if you guys have questions, including the people in the chat, if you have any questions, I'm happy to answer them. And maybe I'll pull up like OneNote or something so that we can do that. So let me keep those. Okay, let me pull up OneNote. Give me 1 sec, guys. Okay. No worries. Okay. So, questions? Yeah. Yeah.
Look at the region and choose it so that it's changing y symbol to x or x to y symbol. Like for the three-dimensional region, how do you change the how do you change from y to x?
Yeah, I don't know. Did you guys see a problem where you had to change, like they give you a triple integral and you have to change the order of integration? Did they give you a problem like that?
My notes, it's just the exact actual values.
Okay.
It was mostly just solving the integral,
Okay.
but
Well, here, let's do one. First of all, to be able to write on this, I think I'll need to actually change how I share my screen. Hold on. Okay, I see the questions in the chat. One sec. I'm going to actually duplicate my screen now, since I'm going to be writing straight on it. Multiple displays. Duplicate these displays. Keep changes. And I'm going to share my screen. There we go. Okay, so people should be seeing this right now. All right, so let's do an example. I'm going to take a region. Let's say let's take a simple region as an example. And let's maybe try to write some integral in both dx dy dz, dy dz dx. Maybe we'll try a couple different orders. I think there are going to be a few too many for us to write all of them, but let's try it in a couple. Let's say this curve here. Actually, I'll just give you the equation of the plane. Oh, how do I erase? It's not letting me erase. That's dumb. Okay. Let's say the equation of that plane there is, what would that be? That's z equals 1 minus x minus y. Right, that's the equation of that plane. Okay? And I want r to be, I want r to be all the points in R3 such that 0 is less than or equal to z is less than or equal to 1 minus xy minus y. Okay, so that's z is between 0 and that plane, but then also it's bounded by, actually I'm not going to write this in set builder. I think that would make this a little bit more challenging. Let's write it in the most challenging way. Let's write it just as bounded by these four planes. Region bounded by x equals 0, y equals 0, and z equals 0, and z equals 1 minus x minus y. So that's the region. Okay, and we're going to write the integral, let's say just the integral dv as an iterated integral. And let's write it in multiple ways. Okay, so first, let's maybe write, let's do the first one as, let's do dz, and then maybe dy dx. Oops. Dy dx. Okay, let's do dz dy dx. Okay, so what's the lower bound on z in terms of x and y? Remember, if we're at the innermost integral, our, can you guys silence that? Thanks. the lower and upper bounds on z need to be in terms of x and y. So what's the lower bound on z? Yeah, it's just 0. Okay, so I'm going to write out a bunch here. So we have dz first. This is z equals 0. And what's the upper bound on z? Yeah, and I'm not going to write z equals. I'm just going to say, yeah, so 0, 1 minus x minus y. Okay, now let's do dy. Okay, so now we're looking in R2. So we're looking in so that's the x-axis. We're looking in this xy plane here. What is the lower bound on y with respect to the remaining variables that have not been integrated with respect to? So that would be x. So we're right here. That lower bound there on y is 0, and the upper bound there, the upper bound on y, is whatever that line is. What is that line? Yeah, 1 minus x. So, and that's 0. So the lower bound on y is 0, upper bound is 1 minus x. And now x, we just take x, lower bound to be whatever the least value that it achieves, and the upper bound to be the highest value that it achieves. Least is 0, greatest is 1. There we go. So that's dz dy dx. Let's do one more, but let's write it in a different order. Okay? So let's do, which order do you guys want to do? Do you want to just reverse it? Yeah. Okay, let's do dx dy dz. Dx dy dz. Okay, so for dx, we're going to go from the lower bound on x in terms of y and z. What's the lower bound on x in terms of y and z? Well, if you look back here, the lower bound on x would be whatever the back of, sort of the back of this plane. Oop, that's not. It's the, it's this back end, right? That's the lower bound on x. And what is that given by? 0, yeah, x equals 0. And the upper bound on x, in terms of y and z, is this plane here. That plane is z equals 1 minus x minus y. Well, z equals 1 minus x minus y. If we isolate the x term, yeah, we get x equals 1 minus y minus z, exactly. So the upper bound is 1 minus y minus z. Now let's do dy. So now we do the lower bound on y in terms of the remaining variables, which is z. So the lower bound on y is just 0. And the upper bound on y in terms of z is given by this curve in that yz plane. And that is y equals 1 minus z. Or z equals 1 minus y. So that's 1 minus z. And lastly, we go from 0 to 1. So, yeah, in this instance, you can write it a couple different ways. This is a simple example, but the same sort of principle applies. You, for that innermost variable with which you're integrating, you write the bounds on it in terms of the variables that you have not integrated with respect to. So for that inner one, dx, we write it in terms of y and z. For the second one, write it in terms of the remaining z. And for the last one, just its least and greatest possible values, yeah.
Can you do an example of a region trapped between a cone and a paraboloid?
Trapped between a cone and a paraboloid? Yeah. Let me check the chat, make sure that everyone's good. Where's the chat? Control-Alt-Shift-H. Chat. Where's the chat? Do we still have people? Here we go. When you take the gradient of f and set it equal to 0, are the two components, so I'm just going to address these real quick. Can a region be neither x simple nor y simple? Yes. Let me show you an example of that. I'm just going to address these questions real fast. So a region can be neither x simple nor y simple. Let's see an example. Oops. So for example, that's a bad drawing, but you get the idea. This region here is neither x simple nor y simple because both horizontal and vertical segments would be broken. And what you could do in instances like this is split the region. For example, if you split the region just down the middle here, then you suddenly have two regions. Let me erase that. So if we call this maybe, oops, that's supposed to be an eraser. Darn it, I can't erase it. Okay, whatever. That's R1. That's R2. Now, R1 is y simple, and R2 is y simple, and you can integrate each of those. So this would be sort of the upper bound on, and in fact, this one would still be nasty because then you'd have to split these. So maybe I would even split it there, and there, and there, and there. And each one of those regions would be easy to integrate over. This one, its lower bound is constant. This one, these guys would be the trickiest, but yeah, the point is, yes, you can have regions which are neither x nor y simple. And another question was, when you take the gradient of f and set it equal to 0, are the two components the two coordinates of a critical point, or is each a coordinate of a different point? The coordinates of the critical point are the x and y values that satisfy setting the gradient equal to 0. So setting the gradient equal to 0 is an equation in x and y, and the critical points are whatever satisfy that. So if you have gradient of f x y equals 0, let's say this is x star and y star. If it's 0 there, then that means x star y star is a critical point. That's the critical point, not the coordinates of the gradient. Okay, good question. Okay, so now we're going to do bounded between what again? A cone and a paraboloid, yeah. So, and do you have a specific, do you mean like, do you have a particular example? Yeah, let's see.
Right here. You looked at this in class. It's equals square root of x squared plus y squared and it's equal to x squared plus y squared. It would look like this. It's one of the.
Oh, I see what you're saying. Oh, geez. Dropped a mic. Yeah, let's do that. Sorry. Okay. Okay. So are you fine with if I use just the exact same example, or do you want to do a different one? Okay, cool. So, I mean, otherwise I would just scale it. Okay, so we're going to, and are we just integrating dv?
Yeah.
Okay, so we're going to find the triple integral over the region R, where R is all points x, y, z in R3, such that, so x squared plus y squared, no worries, see ya, is less than or equal to, z is less than or equal to the square root, was it this? 1 plus?
It was x squared plus y squared, square root of x squared plus y
Here's the square root of x squared plus y squared?
Just square root of x.
I see, I see. Oh, what the hell? Sorry. Oh, God. Okay. Oh, my God. X squared plus y squared. And that's it? Yeah? Okay, cool. So it may be a little difficult to get a picture of what's going on here. Maybe like we could use GeoGebra or something. But I'll try to give you a slice of what's happening here. So z equals x squared plus y squared is an upward facing paraboloid whose vertex is at the origin. Z greater than or equal to x squared plus y squared is all the points that are above and on that paraboloid. So here's that paraboloid. Okay. And points that satisfy this inequality are sort of inside and above that paraboloid. Why can't I change the freaking... This is frustrating. I hate this stupid thing. Okay, I'm just going to use blue then, whatever. Why can't I change? Oh, God. Okay, and this guy is a cone. And they intersect along a circle. And the region in question is this region. I think just for fun, I'm going to pull up GeoGebra here, although I'm not sharing my screen with GeoGebra, so maybe I should share the screen with GeoGebra. Okay, so here we have z greater than or equal to, oh, I need 3 dimensions. View 3D graphics. Okay, so z greater than or equal to x squared plus y squared. Where is it? Z equals x squared plus y squared. I'll just graph both of these. And z equals the square root of x squared plus y squared. And the region in question is the sort of part in between them. It's sort of hard to see, but do you guys kind of see this? It's the part in between these curves. We can actually even sort of go inside. It's inside this part, you see? Inside of here. That's the region over which we're integrating. So it's a little silly. Okay. So I would recommend maybe integrating with respect to z first. And then going with respect to x and y. So let's integrate with respect to z first. Oops. Okay, maybe this time it'll let me change the color of my, yes, okay. So if we integrate with respect to z first, the lower bound on z is not 0, what am I doing? The lower bound on z is x squared plus y squared in terms of x and y. And the upper bound is the square root of x squared plus y squared. It's that cone, right? So dc. Are you guys okay with the lower bounds there? Lower bounds are just plucked straight from this. The trickier part is writing out the lower and upper bounds on the next variable. So if we look in the xy plane, come on. It's not letting me change my ink. Okay, whatever. If we look in the xy plane, then x and y are both integrated over this circle here, right? The lower bound on, let's say x, let's do first with respect to x. Actually, let's do with respect to y. This equation here is x squared plus y squared equals 1. And if you isolate y, you get y equals plus or minus the square root of 1 minus x squared. The positive branch is this part right here, And the negative branch is this part right here. And these here give us the lower and upper bounds on y in terms of x. So we can then lower bound, negative square root 1 minus x squared, positive square root 1 minus x squared. And the last one, with respect to x, it's just the least and greatest values of x achieved on this region, integrating over this region. And so we get negative 1 to 1. Yeah. Say that again? Yeah, so here's the x-axis. This x value here is 1, and back here, it would be negative 1. This is why I prepare these things ahead of time, so that I don't have to subject you to these terrible drawings.
Wait, why is y bounded between negative rad 1 minus x squared and 1 rad 1 minus x squared again?
Yeah, so these guys will intersect. So this intersection up here, oops. If you want to find out what the equation of that curve is, it's where z here equals this. And if you set those equal, so x squared plus y squared is equal to the square root of x squared plus y squared. That's only true if x squared plus y squared equals 1.
Yeah, okay, that makes sense.
So that's how we get that. All right, let me check the chat. Someone said during the second derivative test, what occurs if f(x(x) is 0? If f(x(x) is 0, then you'll automatically have that d is 0. Yeah, I'm sorry, d is negative. If f(x(x) is 0, then d is f(x(x) times fyy, which is automatically 0, minus fxy squared. And if fxx is 0 and fxy is not 0, then d would be negative. If fxy is 0, then it's 0. So if fxx is 0, then it's either a saddle point or it's inconclusive. It depends on the value of d. So yeah, you can have fxx be 0. That's possible. Yeah. Actually, I can come up with an example of one. Let's take fxy equals x cubed minus y cubed. And consider it at 0, 0, consider it at the origin, or just find its gradient. Set it equal to 0, 3x squared minus 3y squared. And you set that equal to 0, and you get xy equals 0, 0. And you do the second derivative test to classify this. Fxx is 6x, and fyy is negative 6y, and fxy is 0. And yeah, actually in this instance, this is inconclusive. If x equals 0, 0, if y equals 0, this is 0, that's 0 anyway. So d here is 0, and fxx was 0. So you can either have d be 0 or d be negative. in the case that f(x(x) is 0. So to clarify. Okay. All right, other questions? Does anyone either in the chat or anyone in the room have a particular example that they would like to go over, or is there anything that they'd just like to talk about a little bit more? More triple integrals? Yeah. Gives a couple other examples of triple integrals? Yeah, yeah, let's take a look.
There was a line with a solid between these two, like hyperbola, and it's not hyperbola, it's like two circles. Like
Yeah, I see. 6 minus x squared minus 2y squared. Yeah. 6 minus x squared minus 2y squared. So, oh, I need to zoom out a lot. Let's do standard view. So now what we're doing, oh, I need to zoom out even more. There we go. Okay, so our region of integration here is the region bounded by these guys here. I want to plot that curve. That's okay. Or maybe let me take the intersection. Intersect F and A. Oh, I can't do that. Tragic. Okay. Well, that's our region, but that's okay. You guys don't have access to tools like this on your test anyway, so. Okay. So, find, is it just dv? Integrating dv? Okay. So we're gonna integrate over the region R, just dv, where z is bounded by x squared plus y squared on the bottom, and 6 minus x squared minus 2y squared on the top. So both of these are paraboloids. The one on the left is an upward facing paraboloid with its vertex at the origin. And the one on the right is a downward facing paraboloid, an ellipsoidal paraboloid, so it's not circular, it's ellipsoidal, and its vertex is at the point 0, 0, 6, so it's shifted up by 6. Okay, so I'm just going to draw a really terrible picture. So here's one of those, and hey, now it let me. Here's another one of those paraboloids. And we're concerned with that region there, okay? The region between them. And actually the intersection here, it doesn't quite look like this. You can actually see in this picture that it sort of curves up and then curves down. But we wouldn't know that, so I'm not gonna draw that, okay? So, but we could expect you to know that it would look something like this, right? That's okay. So let's go for, which direction do you guys wanna integrate with respect to first? What do you think would be the best? Yeah, I think DZ would be a good call too. Writing so the way to, the overall way to choose which order to integrate with respect to is, assuming that it's not a simple region and you don't have something that is impossible to take the antiderivative of, like e to the x squared, then we clearly are looking for a certain one. But otherwise, which order of integration is easiest to write the bounds on? So if we tried to do first with respect to x, we would have to split this into 2 separate regions and add them up. If we tried to do this first with respect to y, we'd have to split it into 2 different regions and add it up. But with respect to z, we can write the lower and upper bounds both in terms of a single function. So dz, let's do dz here. The lower bound there is this green curve, and that is x squared plus y squared. And the upper bound is 6 minus x squared minus 2y squared. Okay, you guys want to do dx dy or dy dx? dy dx? Okay. So dy dx. Okay, so I'm going to do what we did in the last example, which is let's look at the sort of shadow of this region in the xy plane. So it looks like it looks like y achieves its maximums. I shouldn't say achieves its maximums. Y is bounded above and below by this circle, right? If you sort of take the shadow of this, I shouldn't say circle either because it's actually not a circle. It's an ellipse. Let's figure out what the equation of that ellipse is. So the equation of this ellipse, that's going to be given by whenever these two curves are equal. I'm sorry, these two surfaces are equal. And that's x squared plus y squared is equal to 6 minus x squared minus 2y squared. And that gives us 2x squared plus 3y squared is equal to 6. And now isolating y, we get y equals plus or minus the square root of, let's see, 1/3. How do I want to write this? 6 minus 2x squared, it's all right. 2 minus 2/3 x squared. Okay, so that is writing the equation of that ellipse in this implicit form. And here this is, that part of the curve is y equals positive square root of 2 minus 2/3 x squared. And this is y equals negative square root of 2 minus 2/3 x squared. And so those give us our lower and upper bounds. So we have minus the square root of 2 minus 2/3 x squared up to positive 2 minus 2/3 x squared. And now we just take x from its least value to its greatest value. So its least value is, so let's look at this ellipse in the xy plane. So here's this ellipse. I don't know if it's fat or skinny on the x-axis, so I'm just going to draw it, assuming one of them. That's a terrible ellipse, I'm so sorry. It's a little bit better. And we want to figure out what are these values here. Okay, well those values will occur when y equals 0. So if you plug y equals 0 into the equation of the ellipse, you get 2x squared equals 6. And so x squared equals 3. So this guy is square root 3, and this guy is negative square root 3. So in other words, this x value there is negative square root 3, and this x value here is positive square root 3. And so those will be our lower and upper limits on x. And so that is that integral. Make sense? Cool. Let me check the chat. Someone just said how to find the interval for y and x. If you can clarify that, that would be awesome, because I don't know quite what that means. Okay. Other questions, guys? You have one? Say that one more time. Oh, what did I put y equals 0 into? Yeah, so this ellipse is given by the equation 2x squared plus 3y squared equals 6. And to find these, those x-intercepts, x-intercepts occur when y equals 0. So I put y equals 0 into the equation of that ellipse. And so we get the equation 2x squared plus 0 equals 6. So 2x squared equals 6. And so x squared equals 3. And so x is plus or minus square root 3. Okay. Questions? Let me double check the chat. Okay, well, let's call it. Good luck on your guys' exam. And I won't see you guys because I'm not proctoring your exam. Well, I'll see you over webcam. So don't do anything fishy. All right.